Welcome to 9.1. We're going to talk about the basics of hypothesis or significance testing in this section. Significance testing is the second portion of the inference theme, and I'll draw the distinction between confidence intervals in just a minute. For the first activity, if you go to the textbook companion website and click on updated statistical applets and then the reasoning of a statistical test, you will get a screen that looks like this. Should be compatible even if you have occasional Java issues with your tablet. What it's looking at is whether you believe a certain randomly chosen shooter really does have an 80% free throw percentage. So if you hit shoot, it will show whether the person makes or misses the basket, and then the overall percentage toward the end of those 10 shots. I would recommend doing that several times, or maybe even changing the shots to a higher number, 100, 200, and then hit shoot. It won't animate every single one, but you'll be able to see a better idea of the long range or long-term behavior when you do that. And then it's up to you to decide whether you think that this shooter really is an 80% free throw shooter. So if the person does have an overall proportion close to 80, you may conclude, yes, in fact, that is correct. Or if the percentage is way off, either above or below that, you would say, doesn't look like 80% is correct for this shooter. So pause the video for a minute, try that once or twice, and see what conclusions you make. The idea behind significance tests is a little bit different from confidence interval. So a confidence interval is if we had, for instance, no idea of what we thought the free throw percentage of our basketball player was. And so we would take sample data to estimate for an unknown population proportion in that case. The goal of the significance test or test of significance or hypothesis test is when I have some idea of what I think the population proportion or mean is, and I want to test that. In other words, I want to see how likely it is that my previously held belief is correct about the population. The basic idea behind that is if it is unlikely that a certain outcome would happen in a sample, that gives me evidence to suggest that the what I thought was true about the population is actually false. Okay, so in terms of our four-step process, state, do, plan, conclude, that we've done in other portions of this textbook, the first part that has pretty strict rules in terms of what you need to do for a hypothesis test is that you will state the hypotheses. There will always be two of them. The null hypothesis, which is H subscript O. You'll recognize that it's like the H naught, the little subscript O, meaning the initial hypothesis. It is the idea that nothing has changed from what was previously believed. So it would be that the mean is still equal to whatever, or that the proportion is equal to 80% on the basketball player example. When we are going to evaluate our hypotheses, what we're really going to be judging is whether or not we believe this null hypothesis is true. The alternative hypothesis is the other option. So a lot of times this is us saying, we think that the null proportion, for instance, is wrong. 80% is not correct based on the shots that I took with my simulated basketball player. I really think that her overall proportion is lower or is higher just based on my data. You have two options for the alternative, either a one-sided alternative, meaning that I think that the true value is either less than or greater than, or a two-sided alternative saying I'm not going to commit to either direction, but I think that the null is incorrect. I believe the proportion is not equal to 0.8, or the mean is not equal to whatever was previously held. Okay, so for the free throw shooter, here is how the hypotheses would be written. A null is that the proportion really is 80%, or based on my data that I collected, it looks like the proportion might be less than 80%. And then I need to define what that parameter is, so where P is the free throw proportion of this particular basketball player. Another example from the book, two different options for an assembly line factory work. Either the workers would be self-paced, meaning they would choose how fast or how quickly they would perform their task, or machine-paced. The company chose 18 subjects at random. They each did both treatment for a certain amount of time, and then took a test about job satisfaction. So this is a matched pairs design, and we would be testing whether the difference in their job satisfaction was nothing. In other words, that they were equally satisfied whichever pacing method was used. So either the null would be that the average difference is 0, or the alternative, the average difference is not 0. And you don't have to put any kind of personal lens to this to figure out whether I think, well, maybe they would be happier with one way or another. If you look at the problem, it just says, does the job satisfaction differ? Therefore, you just use not equal to, and then define where mu is the average difference in job satisfaction, and I would want to spell out which way I'm subtracting. So for instance, self-paced minus machine paced. Okay, take a look at page 546. We looked at number 1, 3, 7, and 9. Take a look at those problems, see if you can just pick out what is correct or incorrect about the hypotheses given. So based on the first scenario, we would have a null that the proportion is equal to 12. This is Simon looking at whether the proportion of left-handed people is the same at his school as it is nationwide, versus not equal to 0.12. It doesn't say anything about whether Simon thinks it is larger or smaller at his school, so we just use not equal to 0.12 or 12%, and then define P. Number 3, the researcher believes that non-traditional students over 30 years of age, would have a higher satisfaction rating than the traditional age students. So if the average for traditional age students is 115, the null will be that there is no difference between non-traditional and traditional students. The mean of the non-traditional would also be 115, versus the alternative that what the researcher believes that the mean would actually be higher for students over the 30 years of age. For 7 and 9, 7, the hypotheses in terms of the parameters were written correctly, but the null and the alternative were switched. So what was written in the book as the null should be the alternative and vice versa. And number 9 had the equals where it needs to be, in other words, in the null, but everything was written in terms of x bar. And you want to use mu. Once again, that's kind of the curly lowercase m, the Greek letter lowercase m, and not a u. Okay. Under the plan step, it'll be pretty much the same as confidence intervals. The do step is where the next big difference comes in for hypothesis or significance testing. You will calculate a p-value, and a p-value assumes that the null is true and then calculates how likely it is that we would have gotten sample results that we did. So for the free throw shooter, one example that was simulated, into the computer went the idea that someone had an 80% average free throw proportion. Okay, 500 sets of 50 shots each were simulated, and then the stop plot was created. And we look and compare what our example player did versus what the simulation shows. So our example player only got 32 out of 50 shots, meaning that for that one sample, the free throw shooter had a 64% success rate. If you look at our simulated results, only 3 times out of 400 trials did the computer suggest that even if 80% is the center, that they could have gotten that low of a proportion just with one sample. So because that value, that proportion, or that likelihood is so small, that would suggest that if the player does get a 64% without having injury or some other factor adding into that, that maybe they really aren't an 80% free throw shooter. Okay, for the job satisfaction, at this point, this is calculated for you. The average difference ended up being a 17 for the set of data that was carried out by this study, with a standard sample deviation of 60, and the corresponding p-value is about 23%. Okay, so even though a mean difference of 17 sounds kind of big, this p-value suggests that the difference of 17 could have just come up by chance. In other words, if I did the study again, maybe I would have gotten an average difference of negative 15, or then positive 10, and then negative 20. In other words, that overall, for the whole population, there is no significant difference. Okay, so small p-value suggests that the null is wrong, that the free throw shooter is not an 80% free throw shooter, and a large p-value suggests that the null is correct. We never accept anything, but we'd say fail to reject. In other words, we don't have enough evidence to say that the null is incorrect. Okay, so pause the video again. There are some examples on OneNote for some dot plots and histograms to check your understanding of calculating a p-value. See how likely the following sample results are. So pause the video for a minute and take a look at that. Here are the solutions that I got. So the first dot plot, a value of 116. Here is 116. Okay, so there are only 9 dots out of the 40 dots that are 116 or higher. That gives us a p-value of 0.225. In other words, even if my true mean is closer over here to maybe 105, a value of 116 is not that unusual. Okay, whereas this one, X bar of 11 is pretty far away from the center. Only 9 out of 1,000 times did that happen in a simulation. So therefore, small p-value, we think that perhaps the X bar of 11 would suggest that the mean is not really here at closer to about 7.5, between 7.5 and 8. Okay, here's the same thing with histograms. Notice both of these have small values on the left side. In other words, we would calculate the values to the left of the tail just because that's where this X bar fell. Okay, these were to the right because that's where that X bar fell. Finally, after you have a p-value, you're going to make a conclusion in 2 ways. First, you're going to decide to reject or fail to reject the null, and that is based on the alpha level. Alpha level is a predetermined set kind of line in the sand where you say if it's below a certain value, we're going to reject the null. We're going to say the null is wrong. And if it's above the value, we have to fail to reject it. In other words, we don't have enough evidence to say the null is incorrect. We can use any value for alpha. 0.05 or 5% is the most commonly used and the default one that our book uses. So you're welcome to use that on any chapter or AP free response if another alpha value is not given. 10% and 1% are other alpha values that are common, but not as common as 5%. Okay, so we did a little bit of work in the book just to check our understanding, number 13 and 17 in the book, if you want to pause the video and look at that. A p-value of 0.101 was given to us. Translation, there's about a 1.101 chance that I would have obtained an X bar of 125.7 or higher just by chance, would be the interpretation of it. At the 5% level, p is a lot smaller, so of course we would reject the null. But at the 1% level, notice same p-value, the 1% level we'd have to fail to reject, so it's much harder to reject at a 1% level. Okay, if we know that we're rejecting at 1%, meaning it's the p-value is smaller than 1%, we would definitely have to reject at 5% as well. However, if we reject at 5%, we don't really know what we could do at 1% because you have 2 options. Either it's less than 5% but bigger than 1%, where we'd have to fail to reject, or it's less than both, which case we'd have to reject both. But without more information, we can't tell. Okay, last little bit for this section. Of course, whenever you make a decision, you could make an incorrect decision. Type 1 error would be rejecting the null when the null is true, or rejecting the null incorrectly. And type 2 error is rejecting or failing to reject the null incorrectly. So an example, potatoes are being delivered. If less than 8% of the potatoes are blemished, the truckload is accepted or taken in. If more than 8% are blemished, then the truckload is rejected. So we're worried about the more than 8%. Type 1 error would be if the factory sends away the truckload of potatoes based on a small sample when actually only 8% or less were blemished. Okay, so the factory has sent away produce. The farmer would probably lose out the deal. The potatoes could be destroyed. Thinking that they are not going to be able to use, the factory would have to import another shipment of potatoes. Lots of possible consequences. Type 2 error would be the opposite if the factory accepts the truckload of potatoes when there actually is a much higher blemish rate, so the factory loses money they've paid for potatoes that they don't end up using. Okay, the probability of type 1 error is the same thing as alpha level, so if I have 5% as my line in the sand or my cutoff, then the probability that I'm making a type 1 error or rejecting the null incorrectly would be 5%. You won't be asked to calculate the probability of type 2 error. That would have to be given to you. One other thing you do need to know in this section is the relationship between power, which is rejecting the null correctly, and type 2 error, and that is that they are complements. So know that if I am given 1, I can take 1 minus that value to get to the other. So if I say the power is 76%, and really generally 70 plus is considered good, then I can say type 2 error is 24%. Or if power is only 20%, then type 2 error is 80%. To increase type power, we can either increase alpha